Hello AP Calculus people, this is Mr. McAllen. One more time, I think this is the 5th or the 6th video I've done tonight. So what we're going to talk about is finally, as our final video, the conical tank problem. This is one where we have a cone-shaped tank. It's filled with a fluid up to a certain height, and it springs a leak. And well, in this case, in this problem, it's not springing a leak. Water is being poured into it, and we want to know how fast the level of the water is rising when the height is 6 feet deep. So this problem requires quite a bit of work. So what I'd like you to do is first draw and label the diagram I've drawn here so that we have the accurate information on the picture, and then find the static equation that relates the volume of the tank to the dimensions of the tank. I'm going to pause the video, and when I come back, we'll have the diagram all labeled up. Okay, well, we're back, and I drew the diagram, and I hope you like my artwork. It says that the base of the tank is 5 feet, so I'm assuming that is a diameter dimension. It says the height is 10 feet, and then it gives us this volume flow rate of 9 feet cubed per minute. That's quite a bit of water moving into the tank in a minute. So what we want to do is we want to figure out how fast is the water level rising when the tank is 6 feet deep. Our equation that's going to govern this is going to be the volume of a cone. The volume of a cone is equal to 1/3 the area of the base, pi r squared, times the height. Now, right now, this is a two-variable equation. And being that Calculus AB is a single variable class, there's got to be a way that we can consolidate variables, that we can turn this into a single variable equation. Notice we have two variables. We have height and we have radius. We'd like to switch this to just be one variable. Either choose radius or choose height. So what I'm going to do is I'm going to suggest that there is a connection between the radius and the height, and I'd like you to use your knowledge of similar figures to figure out what that relationship is between the height and the radius. So I'd like you to talk about that with your friends, and when you come back, I'm going to have the answer, and hopefully our answers are similar to each other, if not the same. Okay, well, we're back, and the relationship is, if you look at the cone from the side, is the diameter is 5 and the height is 10. And this proportion will be the same no matter what the height of the water level is. So the diameter will always be half of what the height is. So for example, when our height is 6, the diameter will be equal to 3. And this ties together the radius to the height. If the diameter is half the height, then the radius is a quarter of the height, because you should realize at this point in your math career that the radius is half of the diameter. So what we're going to do is we're going to use that to rewrite our volume of the cone equation. It's 1/3 pi r squared times h. So I'm going to substitute in for the radius the equation for height. Now I have a function that is solely a function of height. So I have 1/3 pi. I'm going to have h squared over 16 times h. My final equation for the cone for this problem is going to be pi h cubed over 48. Now that we have our static equation, I would like you to find your related rate equation. So I'm going to pause the video and let you guys find dv dt in terms of the height. Okay, well, we're back, and dv dt is equal to the derivative of pi h cubed over 48 is equal to 3 pi h squared over 48 times dh dt. Now I'm going to zoom out so we can look at our given information again. Hopefully it all fits on one screen. And now all we need to do to solve the rest of this equation is to plug the information into the proper place. It said, how fast is the water level rising when the water is 6 feet deep? So we know our dv dt was 9 feet cubed per minute. We know that we had 3 pi. The height was 6, so I'm going to square that. That's over 48 times dh dt, and now I can just solve directly for dh dt, and the rest is arithmetic. So we have 9 feet cubed per minute, and I'm going to divide 3 pi. I have 36. I have 48 in the bottom, which when you divide by 48 in a fraction, you can multiply by the reciprocal. Well, 36 over 48 is going to be 3 over 4, so I have 9 over 3 pi, 3 over 4, and like I said before, the rest is arithmetic. This will be 9 over 9 pi over 4, which equals 4 over pi, and that will equal our dh dt. Now the units of dh dt are going to be in the same units that are, well, not the same units, but in the units that, well, our volume was in feet cubed per minute, so our dh dt units are going to be in feet per minute. So this is quite a rate of change for the volume. This is going to be dh dt at that moment will be 4 divided by 3 is about 1, well, 4 divided by pi is going to be a little bit over 1.3 feet per minute. So that's quite a quick change of height for this moment with this cone problem. So hopefully this has helped you understand how to work through the cone problem, and please like or subscribe to this video channel, and comment on this video, and let me know what else we can do to help you understand related rates. Thank you very much, and have a good day.